All right, good morning, everyone. Thank you for coming back for day 2. We are about to get started, and I am delighted to introduce our first speaker, who is my co-organizer, Dr. Victoria Stodden.
Thank you, David, for the introduction, and thank you, everybody, for getting here so early. So I'm not seeing the slides in front of me. So this morning I am going to take advantage of the fact that I happen to be the first speaker, and what I was hoping to do in this talk is actually respond to some of the issues that were raised yesterday throughout the entire day of discussion. So I have a couple of ideas that I wanted to throw out to you for discussion, and I'm thinking about the next step. So we have issues that were raised. What can we do that's actionable to try and start solving these problems, and what are some of the things that are actually taking place and being done? Okay, so I'm not going to spend time on this. We spent time on it yesterday. Just to remind you that, at least in my mind, I'm thinking about reproducibility in terms of sort of traditional empirical aspects of reproducibility, issues of irreproducibility that come from statistical methods, perhaps being misapplied or applied in ways that fall short of reproducibility concerns, and then the computational aspects of reproducibility. Much of my own research falls into the third category, the computational aspects. So that's where I'm going to place a lot of the thinking throughout the rest of my short amount of time talking to you. It doesn't mean that the other aspects are somehow less important, but that's where I'm going to focus today. Okay, so I'm going to read this to you, so don't worry about taking a look at it. I wanted to start with a thought experiment. So imagine that we have solved this problem. Imagine that we're researchers several years out, and we are doing our research and understanding our scientific stock of knowledge in a world of radical transparency. So at a click, you've got code, you've got data, you've got methods, you've got all sorts of information at your fingertips, whatever we talked about yesterday that you might dream that you might like with the publication of scientific claims. So we could do things like show me a table of effect sizes and p-values for all phase 3 clinical trials for melanoma published after 1994. So that could be a query that I could just visit on the scholarly record and get this table returned to me. I could also query the scholarly record to return all the denoising algorithms that have ever been applied to the very famous and widely used Barber image in signal processing. And when you return the list of those algorithms, give me also the citations that have used them. What articles have used them? I'd like to query the scholarly record to get a list of all the classifiers that have been applied to the famous acute lymphoblastic leukemia data set, and give me misclassification rates as well when those classifiers were applied. I'd like to query the scholarly record for a unified data set. So, for example, give me all published whole genome sequences identified with the BRCA1 mutation, for example. I could also do something like randomly reassigning treatment and control labels to cases in a published clinical trial, and then I can calculate effect size given that random reassignment. I could imagine doing this many times and then having a histogram for effect sizes that are actually detected in that clinical trial. So I could also imagine doing this for, say, all the clinical trials published in a particular year, and I can look at all these effect sizes side by side. So all of those queries, I wanted to push your imagination because all of these queries are exceptionally difficult, if not impossible today. And I believe these queries are pretty natural for a researcher to actually want to visit on the scholarly record. And furthermore, I think that we are going to a place where we'll be able to actually do these queries. Okay, so I talked about computational aspects and how perhaps better tools on the computational side can help enable these aspects of reproducibility that we started to draw out yesterday. I'm not the only one who's noticed that these are issues in how we actually carry out and how we communicate our research. So I put some of the current tools up there. This is a hopelessly and always incomplete list. I divided them into things like research environments, workflow systems, and dissemination platforms. This is also a very rough sort of cut for what these tools are doing. However, I spent some time hot linking them so you'll be able to click in and actually look at the tools. But one thing I do want you to note is just about all of these tools to enable reproducibility and sort of help our computational discovery. Almost all of them just were developed by academics and researchers who were worried about the problem, almost always on the side of their day job. There's a couple of exceptions in there. Gene Pattern, for example, had Microsoft investment in it and so on. There's a few exceptions, but by and large, these are researchers who've just noticed a problem and then taken active steps in the tool space to start to solve the problem. So I find some of these are just very, very impressive. I'll just mention quickly, I've been involved with Run My Code and Research Compendia that are up there, and I'm going to talk a tiny bit about Wholetail that is up there too that I've also been involved in, but the other ones are nothing to do with me. Okay, so thinking about our computational aspects of the research, and one of the things that came out yesterday is that computational aspects are in all sorts of scientific research, even ones that you might think of as not traditionally computational, like clinical trials type research, where you are gathering data on different groups and testing between the groups. There's still a computational component. You've probably got, at minimum, some R scripts there that are doing the analysis. So here are the trends that I see. So I believe that across all scientific disciplines, the projects that we launch are going to be increasingly computationally ambitious. I think it's not crazy to say that we're seeing fairly typical PhD theses produced today that use about 1 million CPU hours. And this is something that's only going to increase. So the ambition and the complexity of the computational projects that we're going to be launching as scientists is only going to scale up. I believe also, based on our discussion yesterday and other discussions, that research computing will become dramatically more transparent. We are going to move away from a system where we have different tools that we rely on. Something goes through email, it goes through Dropbox, then it maybe goes through RStudio, and we've got these sort of disconnected tools, and then we share them in a different way on one of those platforms, for example. And I believe we'll be able to resolve these transparency issues and end up with dramatically more transparency around the computational aspects of our research. So it seems like these trends might be antagonistic at first. We want to do a lot more with the computation, and yet, in a sense, we're asking more of it for these levels of transparency. However, I think the key insight here that's going to enable us to resolve this problem is that the transparency will enable us to launch those much more ambitious jobs and enable the more structured way that we manage and carry out the computational aspects of our work, bringing in things that are desirable, that we want, like reproducibility, for example, ability to reuse, transparency, and the ability to verify the findings. Okay, so some of the tools that were on that sort of very busy slide, the hot linked slide, start to define experiment definition systems. And I think this is an important concept for how we go forward supporting computational research and inference from data. So we can define and create these experiment definition systems, and what they will do is manage the conduct of these massive computational experiments, and also expose the data, expose the analysis, and bring us to that world of much more radical transparency than what we have today. Okay, so the better transparency allows people to run more ambitious experiments, and the computational experiment infrastructure allows researchers to be more transparent. So we see now these reinforcing trends starting to come into play. Okay, so develop new infrastructure to promote good scientific practice downstream, like transparency and reproducibility. So traditionally our tools, if we look at the tools that generally we use for scientific research, many of them were not created organically for the scientific community. And the scientific community, as we heard in the discussion yesterday, is very special in terms of the needs it has from its computational environment. It has extra needs for sharing information and sharing a transparent version of what they're doing with the larger community. So we can build this in a sense. We can build in practices. We can maybe try to automate aspects of reproducibility that we would find desirable as scientists. Maybe we can even do this in a way that is largely seamless and doesn't interfere with the research or the sort of the time that the researcher is putting into carrying out the experiments. And we can make, I believe that we can make a lot of arguments about how wonderful this would be for science and how transparency, reproducibility are bedrocks of our scientific research. But really, when it comes down to it, what we need to do on the tools side is just make life easier for the scientists. So they would use these tools not because we made very compelling arguments about how this is a great thing to do, but because it makes them more efficient, it enables the productivity of their work, and it enables the discovery. So really, it comes down to the transparency being useful as part of managing and launching these jobs. Okay, so I just threw out a few factors to think about what we might like to see in these architectures that support science or where people are actually carrying out their research. We want to capture crucial computational information. There's quite a laundry list from yesterday about aspects that people would like to see transmitted with findings that come from the computational aspects of the work. Maybe we can even automate some of this. Some of these tools do step in that direction, the ones that I pointed out on the previous slide. I think it would be great if we embedded legal information around licensing and reuse that permitted reproducibility and reuse in a very seamless way that we're used to in the scientific community. I'll talk a little bit more about that in a few minutes and how, without taking proactive steps to address the intellectual property issues, we end up with a lot of stuff that's really not reusable. We need to think about things like persistence and archiving of these artifacts or these computational details that have perhaps been saved in an automated way from carrying out that job in this experiment definition system. And then thinking further about how do we find these artifacts? So if you have a publication, how do you dig in and see something like the underlying data or the underlying software that support those claims? So setting up those links and thinking about how we actually discover those artifacts that are associated with a scholarly record. So if you think back to the first slide with the thought experiment about queries I might visit on the scholarly record, that intimately depends on the data and the software and methods and so on being linked to the claims themselves and the publications themselves. Okay, I just wanted to mention also that February 25, 26, so really only a couple of weeks ago, National Science Foundation had a workshop. They called it Robustness, Reliability, and Reproducibility in Scientific Research. I mentioned because there are concurrent discussions where there are similar and overlapping themes that are coming up and reflect these sort of almost like ideals that we'd like to see baked into our experiment definition systems. Okay, another workshop that I wanted to mention is from February last year, about a year ago. So the Arnold Foundation funded a series of workshops. This was the third one in the series around reproducibility. This was the first one to look at the, sort of directly try to assess the role and importance of code and software and how methods are actually embedded in, we didn't call it experiment definition systems, but embedded in the research process and the research pipeline. So what we wanted to do was discuss ways that we could actually think about capturing those methods and what the actual steps were done. We heard a lot of discussion yesterday about the importance of even how do you pre-process your data? What have you done with outliers? How have you merged your data sets? What decisions were made? And capturing all those small details that can be very impactful on the findings and on understanding those findings. So we had a robust discussion that Marcia was a chair of the workshop, and we brought together many stakeholders. And through the discussions, we ended up with a series of recommendations, 7 recommendations that were published last December. So enhancing reproducibility for computational methods. Again, I encourage people to think very broadly about computational methods and how they actually interact with research discovery. It's something I think is extremely pervasive across all types of research in many disciplines. Okay, so I'll just quickly mention the recommendations. And I mention them in the context of thinking about systems that support research that could bake these in some sense. Okay, so the first one's kind of obvious: sharing data, software, workflows, details of the computational environment in open repositories, open trusted repositories. The information that you would need in a particular context to evaluate that claim. Our second recommendation, create persistent links in the published article itself that go to these artifacts like the data, software, workflows, the aspects of the computation and the experiment that are needed for verifiability. Attach unique identifiers, have versions, have snapshots. That's something that came up yesterday. When you're publishing a claim, it's imperative that we're able to go back to that snapshot of the data or that snapshot of the code. Even if it turns out that people subsequently find mistakes or errors or whatever it is, that's, in a sense, the sort of process of record that's associated with that publication. We need to cite this stuff. That was our third recommendation. So we want to encourage the sharing of these digital artifacts, and to do so, we need to be able to cite and track impact of and reuse of these methods. So for data sets, for software, for workflows, for example. Okay, we also, our fourth recommendation was to start thinking as a community around what type of documentation or sort of decorations needed to travel with these artifacts to make them useful in the community. Okay, recommendation 5. Perhaps journals can check this stuff before publication. So even do different levels of checking of the reproducibility. We talked yesterday about the distinction between sort of running code on data and checking that you can come up with figures and tables that are in the publication. So that's something that, if done in the context of an experiment definition system, the way I'm trying to present today, might be actually fairly straightforward to actually run as a pre-publication check. That's ambitious for today, but there are ways that journals can check at least that the data's out there, code is out there that are associated with the publication. Okay, our second last recommendation was to use open licensing to facilitate the ability of people to actually use the code and reproduce the actual results themselves, or extend the code, for example, and the data. And we also, in our last recommendation, we recognize that the solutions here are not always obvious. They can be actually quite nuanced, and there's certainly not one solution that will fit and support all different types of inquiries in different types of fields. So in that vein, we suggested to the community at large, but particularly to funding agencies, that we initiate programs of research around reproducibility to address some of the questions that arise as we start to move towards a more transparent scientific research environment. Okay, so one of the things that we did, so I mentioned that perhaps journals can have a role in, or at least they're one of the stakeholders in terms of bringing about this world of radical transparency. So in September, I wanted to just mention an example. So in September 1st of last year, the Journal of the American Statistical Association, Applications and Case Studies, implemented a requirement that data be available and supporting software workflows, all those artifacts for reproducibility, are available prior to publication. So I am one of 3 associate editors for reproducibility that's charged with making sure this happens. So one of the things that, so we had a lot of discussion about what that would really mean for authors. And how do we do things like check the existence of this work, even it's not obvious necessarily what qualifies or what doesn't. So we're in the process of fleshing out how this policy actually works. One of the things we did is we took this sort of artifact template or sort of research description template that is being used in some computer science conferences, and we adapted it to the JASA ACS environment. So this template on the right I took from an archive paper, and it's just an appendix put on the back of the submission to a conference, and it has a very structured way of asking information about the project. So for this particular project that it's from, this is in a high-performance computing context, and they give all sorts of information. You can see an abstract about the artifact. So in this case, it was software that was being made available, a description, metadata, computational information, runtime information, what the community actually thought was important for understanding those computational aspects of the work. So you can see, it's a little bit small, but there's a description of the experiment workflow and how to actually run the results. So we have a version of this adapted for the statistics community that authors complete to tell us where the data are, what else we should know about the data, software, workflows, and these other aspects. So we're in a position now where we're testing out to see how it works, and we're sort of piloting in a sense. But this is an example of how journals can start to take these steps towards a greater transparency in our research. Okay, I wanted to just spend a little bit of time, as promised, on some of the legal issues around sharing. So I'll start with software, and there are certainly legal issues around data as well. The intellectual property that travels with software and to some degree with data is enshrined in the Constitution. So it's something that as a community it's not going anywhere, and we're going to have to work with it. So in the Constitution it actually says to promote the progress of science and useful arts by securing for limited times to authors and inventors the exclusive right to their respective writings and discoveries. Okay, so the way that's been interpreted through Congress over the years is, in a sense, copyright is default anytime you express your original ideas in a fixed form. And this is something, there's a nice saying, so they say that copyright follows the pen across the page as you're writing. So you can imagine copyright adhering to not just your written articles, but also to software as it's being written to some degree, as I'll discuss, in data. So what happens with copyright is you end up in a situation where the author is highly protected and their expression of their ideas is highly protected. And the analogy that I like to make is if you imagine yourself, say, at a bus stop or whatever it is, and you notice someone next to you sort of scribbling furiously away, and you sort of maybe like peek at what they're writing, and you see that there's this very beautiful poem emerging on their notebook. So the fact of copyright following the pen across the page makes it so that you can't, in a nefarious moment, kind of look at it and sort of copy what they're doing. The fixed form of that idea is copyright to that person, meaning you need to ask their permission in order to do that. So in that sense, it's sort of, I think, kind of intuitive what copyright does. However, when we translate this to the scientific context, where we expect citation but freely share ideas and our work with the larger community, it's not a fit, right? So I've done some work to try and think about how can we make it so that intellectual property aspects don't interfere with how we might naturally behave and want to use artifacts as scientists. And also we can do this in sort of a seamless way where we don't have to spend a lot of time thinking about it. Okay, so copyright, as I mentioned, it secures exclusive rights to the author to reproduce the work and also prepare derivative works based on the original. So those are both things that are considered very good in scientific research. It's very good if someone can reproduce your results. That's something that we would like to enable. And it's also very good if someone can take your work and prepare a derivative work. So for example, extending your code to their application context, or using your data with a new data set and then actually deriving new results. These are all sort of very obvious things that we would consider very good and productive. Copyright blocks them. Copyright's a limited time, so the author plus 70 years after they die, the author's life. And so that's effectively infinite if you think about sort of the life of software, for example. There are some exceptions and limitations to copyright, like, for example, fair use. They generally are confined to snippets and wouldn't extend to the complete set of artifacts that we would like to use in a fully transparent, for example, scientific research environment. Okay. So I also mentioned patents. So patents and copyright are the two main forms of intellectual property that would be visited on us in our work. As I mentioned, copyright's default. That's something that we just would need to address as authors. Patents are not default. They need to be sought, but they interact with our work in a kind of a unique way. So patentable subject matter, it has to be a new and useful process, machine, manufacture, composition of matter, or any new useful improvement thereof. So we have our sort of classic 3 criteria that apply to patents: novel, non-obvious, and useful. So you might be thinking, okay, so maybe that interacts with some of the research that I'm used to, but how does it exactly interact? Well, one of the key ways is through software patenting. And as computational methods become more and more the basis of discovery, scientific discovery, we start to perhaps interact more with the patent system. So the United States Patent and Trademark Office, their final computer-related examination guidelines say, a practical application of a computer-related invention is statutory subject matter, meaning you could seek a patent on it. The requirement can be discerned from the variously phrased prohibitions against patenting of abstract ideas, laws of nature, and natural phenomena. So of course you wouldn't patent a mathematical formula, but the implementation on a machine is potentially patentable. So that's 2 ways that IP law starts to interact with the work that we're doing. Okay, so you could say, well, I won't seek patents, or I'll do it in such a way that doesn't interfere with the sharing of my codes or my research and doesn't mess with your vision of this future of transparency that you're describing. So many researchers are in institutions such as universities, and the institutions in 1980 were charged with using the patent system to facilitate transparency in inventions that were taking place within the university. So that's the Bayh-Dole Act in 1980. 1980, of course, they weren't thinking, I'm sure they weren't thinking about computational methods and software in 1980 in Congress. But the idea was use licensing of patented material from inventions within the university to enable a greater transparency. So industry could look at patent records versus having to somehow traverse the scholarly record or have an in somehow to the ivory tower to get at these inventions. So that was the idea. So Bayh-Dole gives federal agency grantees and contractors, so that might be their universities and institutions, title to government-funded inventions, and it charges them with using the patent system to enable disclosure and commercialization of the inventions. So if software becomes something that the universities have an interest in patenting, like, for example, the software that might underlie some of our discoveries, then that is something that we need to navigate in terms of how do we align that with this world of radical transparency that I'm advocating. Okay, so I'll mention data, as promised. So we do have a Supreme Court case from 1991 that asserts that raw facts are not copyrightable. The case is called Feist. And I highlight this because it raises sort of a little bit of complexity in copyright law and how it interacts with research. Raw facts are copyrightable in Europe, for example, and in other parts of the world. So I would guess everybody in this room has had or currently has an international collaborator. So if you think about sharing data that are under, from a collaboration that might be under different intellectual property regimes, not having copyright adhering to raw facts here in the US, but in Europe having a copyright, that's something that needs to be negotiated for the data's release and reuse in these different jurisdictions. So I also wanted to step back and say that court case discusses raw facts and applies copyright to the copyright discussion to this notion of raw facts. But if we think about the type of research we do today, I mean, this was 1991. In my mind, it's not even clear necessarily what a raw fact is. Is it something that comes from an instrument measurement, or is it something that's the product of our research and inference from the data? So that's not fleshed out in the courts. So we also have this ambiguity about raw facts and the application of copyright and how it actually starts to interact with data. One of the ways it does interact is that court case Feist limited copyright in data to the original selection and arrangement of these facts. So they were in that case, they were talking about phone books and people's sort of address information and how it was displayed in the phone books. But original selection and arrangement of raw facts, if we think of sort of data sets and arrays, in a sense, we do this all the time, right? If we merge data sets or cleverly select variables upon which to do our analysis, maybe feature selection in machine learning might have an overlap with this type of thinking. It's all not legally clear. So it can be sometimes a point of contention around how copyright actually interacts with data in the US as well. So these things are murky, and one of the things that I was hoping to do with some of my research is start to parse some of these issues and make it easier for researchers to just share and reuse without actually thinking too much about the legal implications of what they're doing. I wanted to mention privacy in data. This was another topic that came up yesterday in data sharing. Of course, there are legal barriers to sharing certain types of person identifiable information, like health information or student school records and so on. And we go through IRBs for any work that touches humans, so any type of human subjects research. And there are lots of privacy implications that are coming through for, say, Facebook data or Google data, as well as the proprietary issues. So we start to navigate this legal landscape when we come to thinking about this world of transparency. And it's a landscape that has been imposed on us from sort of other vantage points than the scientific vantage point. Okay. All right, so I just wanted to mention one solution that I've worked on, at least for the copyright part of sharing, and it borrows ideas from open source software. So this is a picture of Richard Stallman, who developed our first open source software license, the GNU public license. And what Stallman noticed was that for me to, if you think about that poem example, and imagine the person's writing software, so all the same, copyright law applies. And if I wanted to use the software that person was writing, like I said, I would have to ask their permission. So Stallman's genius in developing open source software licenses is he said, well, why wait for someone to ask permission? I'll just hang my permission right on there. And so people don't have to talk to me. I've just sort of pre-permissioned the use of these copyrighted materials. It doesn't remove copyright, but what it does is it says, well, here's how you can use it, and I'm just giving this set of permissions to the community or whoever might want to use it. And so since that innovation, which is one of the core reasons the open source software was actually very successful, is his GNU public license. But since the development of that license and that breakthrough, there are now hundreds and hundreds of licenses, a sort of pre-permissioning that has been written for many different contexts, including software. So there's lots and lots. So the idea would be, can we use any of those licenses that have already been developed, and can we do this in a default way for scientific research? So my answer is yes, so that's what's on the slide. So let's do something that aligns with our norms. So our norms tend to be use my work, products of my research that I'm freely making available to the community as you like, for example, furthering research or commercial applications. But what I want is credit and recognition, and we traditionally do that through the citation, right? So that's our normal way that we share ideas and we cite them in the next publication, for example. So what that would mean is on our media components of what we write, so the text that we write, figures, tables that we generate, we could put what's called the Creative Commons Attribution License, which essentially says, do what you want with it, but I do want attribution for this. The Creative Commons licenses are on media components. They don't extend to software, so we need software-specific licenses to do the same thing in this for software. So a recommendation is to use the what's called the MIT license or modified BSD license, which essentially does the same thing in the software realm. So it has this attribution component and is very permissive in terms of how you reuse and use that software downstream. Because of the issues that I outlined in data, this possible nuance and or residual copyright that can actually possibly might adhere to some of the data sets that have been created for science. I'm advocating using what's called the Creative Commons 0, the CC0 dedication to public domain. So just say the copyright is complicated here, so we're going to put it in the public domain and make this data freely available to use. So the idea here is to remove the barriers that IP law, just by its very nature, put in front of reuse, reproducibility for scientific publications. And so our IP framework is realigned with our scientific norms. Okay, I wanted to mention that this is something that's coming up in other areas too. So this report, Legal Issues for Integrated Data Systems, Finding a Way Forward, just came out on Tuesday. And I was one of the authors. And what we do is we come up with some legal agreements or templates to allow the use and combination of very private data, so local government data, state data for things like matching case studies or following potential child abuse victims. So we could look at, say, school grade patterns matched with benefits from the state, for example. I mean, we, not necessarily all of us, but people who are permissioned to be able to do that. So there were legal agreements about how the states would actually contribute to this integrated data system, and then as a user, agreements about how they would actually use or extract the information or sort of analyze the information that's in that data system. So this is something that these issues start to come up in all sorts of different places, even when reproducibility is not sort of the primary goal of collecting the data together. Okay, so we're still in this environment where we see these computation becoming more pervasive in our research, and also where we start to see these tools for managing the computation actually enabling the reproducibility and the best practices. So I'll just finish by mentioning a project that I'm working on with a group of collaborators called Whole Tail. So our idea with Whole Tail is, can we do something that brings together the tools that scientists currently use? I sort of mentioned earlier how you might use things like, say, Jupyter notebook environments. You might use something like remote compute power. You might use data sets that exist in, say, Sloan Digital Sky Survey or sort of remotely. And how do we kind of start to put some infrastructure, some computational glue to create an experiment definition system that allows the researcher to manage their scientific research and their entire flow, and also can do things like capture aspects that enable reproducibility and enable transparency when the results are actually published. So we want to integrate all these tools to simplify their usage and also promote best practices, which is also something that the discussion is evolving. So we have an NSF grant for 5 years. We just got it in March last year, so we've had it 1 year. And so the idea of Whole Tail, okay, so just a note, those are my collaborators on the project. So we're exposing tools that researchers already use, like, for example, Jupyter or RStudio. Both of those came up in the discussion yesterday. And then creating that software glue, or sort of the cyber infrastructure that allows the different aspects of the computational pipeline to be knit together in a coherent whole. So this goes from data, or wherever you start your research, right through to publication, and produces objects that can be integrated into the scholarly record or linked and referenced from a publication. And our key idea is embedding, maybe not best practices, but at least better practices into the research experiment environment where people are actually carrying out the research themselves. Okay, so Whole Tail, the idea was this sort of almost soup to nuts capturing of that entire experimental workflow. So being able to go from something like which data set you may have started your work on, how you actually did all those sort of data preparation aspects that were talked about yesterday, including outliers, how do you deal with missing values, how do you combine data sets, and so on, right through to the analysis and the extraction of information from the data set itself. And then those objects would be seamlessly integrated into publications and into the scholarly record. So we sort of see this, almost this life cycle, right, of being able to therefore hand off those objects to other researchers for verification, for reuse, for a variety of different purposes. Okay, wholetail, we also wanted to create infrastructure that served all sorts of sizes of research across the scientific community. So, for example, we didn't want to create this sort of instrumented system that only served sort of high-end, very sophisticated computational researchers, for example. So the wholetail also refers to what can sometimes be called the long tail. So even people who are generating one-off comparatively small amounts of data for their research would be able to benefit from using this system and having this integrated pipeline. And we wanted to enable discovery across all sorts of different scales of research. So that's my illustration of the long tail. Okay, so in conclusion, I think that we are on a trajectory of being able to develop the tools side of the solution, which is, of course, not the complete solution, but something that I chose to discuss and focus on in my few minutes today, but develop that tool side in a way that enables researchers to carry out research that they would like to do in a more efficient and more productive way. Also having the benefit, if we think about what these systems can enable, to sort of push the needle a little bit on reproducibility and transparency in a way that is seamless and useful for the researchers and for the larger research community. So I wanted to highlight a few of the things that I think are important moving forward on the computational infrastructure side to support reproducibility. So thank you. I'm happy to take questions.